All right, for section 7.1, we're going to discuss the properties of the normal distribution. Before we get to the normal distribution, we're going to first just talk about uniform probability distribution. So a probability density function is an equation used to compute probabilities of continuous random variables that must satisfy the following two properties. The total area under the graph of the equation over all possible values of the random variable must equal 1, and the height of the graph of the equation must be greater than or equal to 0 for all possible values of the random variable. That is, the graph of the equation must lie on or above the horizontal axis for all possible values of the random variable. So essentially, that's just telling us that the area underneath the curve has to total up to 1, regardless of the shape. To look at this a little bit more, the area under the graph of a density function over some intervals represents the probability of observing a value of the random variable in that interval. So let's make that make a little bit more sense. So we're going to look at our example. So suppose the following density function represents the chance that your friend is X minutes late meeting you. And with this, we're looking at between 0 and 30 minutes late, and that they are just as likely to be 0 minutes late as they are 1, 2, 3, 4, up to 30 minutes late. So if we want to find the probability that our friend is going to be between 15 and 25 minutes late, we're going to have our nice little distribution here with 0 through 30 minutes. Well, we know the area here has to equal 1. And I know that from here to here is 30 long, so I know 30 times the height has to equal 1. So I'm trying to figure out how high this is. So to solve for h, we're just going to divide both sides by 30, and we're going to get h equals 1/30. And again, this is for a uniform distribution that everything is equally likely to happen. So if we want to look between 15 and 25 minutes, we're going to have our 15 minutes here, 25 minutes, and we're looking for the area between these two. So to find the area, because there's a rectangle, we're just going to do length times width. So from 15 to 25 is 10, but if you weren't sure, we would do the 25 minus the 15 to get our 10, and then times this 1/30. So we're going to have 10 times the 1/30. So that's going to give us 10/30, or 1/3. So the probability that our friend is going to be between 15 and 25 minutes late is 1/3. The probability that our friend is at least 20 minutes late, again, we're going to have our same distribution. So 0 to 30, our height is 1/30. And again, because we know that the area here has to multiply to 1, or the area has to equal 1, so that our length and our height, so the 30 times 1/30, this will give us 1. So at least 20 minutes late. So 20, and the at least, so 20 minutes or more. So that's going to be this area over here. So we're going to have our 30 minus 20 and get 10 for this right here, that length. And again, we're going to have the 10 times 1/30. And it's going to end up giving us that 1/3 probability that our friend will be at least 10 minutes late. So find the probability that your friend is no more than 5 minutes late. So for C, again, we start out by drawing our distribution. So we have 0 through 30, so they can be up to 30 minutes late. And no more than 5 minutes. So if 5 minutes is here, we were looking for them to be 5 minutes or less. Oops. There we go. So we're looking for this area here. So it's going to be 5 minus 0, or just 5 for the width here, times 1/30. So we're going to get 5/30, or 1/6. So the probability that our friend is no more than 5 minutes late is 1/6. All right, so with this example, we started with 0, because we're talking about how many minutes late. However, we don't have to have 0 as our first number there in the corner. So the uniform distribution, suppose the reaction time x in minutes of a certain chemical process follows a uniform probability distribution, with x being between 5 and 10 inclusively. draw the graph of the density curve. Well, we're going to have 5 here because this is the lowest it'll be, and a 10 here, so that'll be the highest. Now we need to figure out the height. We're not considering just the 10, because again, we need to be able to multiply the length and height to get the area of 1. So this has a width of 5, because the 10 minus 5 is going to give us 5. So this has a width of 5, then the height must be 1/5, because we know that 5 times the height has to equal 1. So 5, which is the length here, times the height here is going to equal this area of 1. So the height is going to be 1/5 whenever we solve for h. And so now we have the general idea of what's going on. This is our density curve here. And then for B, what's the probability that the reaction time is between 6 and 8 minutes? So we're going to still have our 5, our 10, and our 1/5. And we're going to have that for all of these. So I'm going to go ahead and label them. And now to look for our between 6 and 8 minutes. So 6 to 8 minutes might be something like this. We're looking for this area here. So for B, that 8 minus 6 is going to give us 2 for how wide this is. So we're going to have 2 times 1/5, which is going to give us 2/5 or 0.4. So the probability that the reaction time is between 6 and 8 minutes is 0.4. For C, the probability the reaction time is between 5 and 8 minutes. So 5 up to 8 minutes. It's going to be this area here. So the 8 minus 5 is going to give us a 3. So we know that this is a length of 3 or a width of 3. So 3 times the height of 1/5 is going to give us 3/5, which is going to be a probability of 0.6. So the probability the reaction time is between 5 and 8 minutes is going to be 0.6. For D, what's the probability that the reaction time is less than 6 minutes? So we have our 6 minutes here. So to be less than that, we're looking for all the area here. Now remember, this isn't from 6 to 0. This is only from 6 to 5. So we're going to have that width of 1 times 1/5. So we're just going to have 1/5 as our probability, or 0.2. Okay, now let's talk about the normal curve. So a continuous random variable is normally distributed or has a normal probability distribution if its relative frequency histogram of the random variable has the shape of a normal curve. So you'll also hear this referred to as the bell curve. There are several characteristics that are going to be really important to help us solve using the normal curve. So it's symmetric about its mean mu. So mu is going to be right in the middle. The mean, median, and mode are all going to be the same value. It's going to have inflection points, which just means that the direction the curve faces changes at mu plus and minus that 1 standard deviation. The area underneath this curve is 1. The area to the right of mu is the same as the area to the left of mu, which means that this curve is split in half. So half is here, so 0.5 area and 0.5 area. Again, the fact that it's symmetric, we could figure that part out. As x increases without bound, the graph approaches but never reaches the horizontal axis. So as x gets larger and larger, this line's going to never actually be 0. It's going to be really close to 0, and for all practical purposes will be 0. But it doesn't technically ever touch. It's the idea of this blue line approaching an asymptote. The empirical rule states that about 68% of the area under the normal curve is between 1 standard deviation to the left and right of mu, so this would be 68% here, and that there's 95% between 2 standard deviations. So 2 standard deviations is going to hold 95% of the data points, and between 3 standard deviations, we're going to have 99.7% of the data points. And to do that, we're starting with the mu. We would add and subtract our standard deviation, or our sigma. So here are a couple of different normal curves. So this first one in pink, it's going to have a mu or a mean of 0, and it's got a standard deviation of 1. So going out 1 to the left and right, there will be 68% of the data points between -1 and 1 for this pink curve. For this blue one, we have a mu or a mean, which remember, mean, median, mode are the same for this. It's going to be a 3 and a standard deviation of 1. So from the mean out 1 standard deviation, we would add the 1 and subtract 1 to go to the left and right 1 standard deviation. And then here for our second example of B, these both have a mean of 0. However, they have significantly different standard deviations. So for the pink one, there's a standard deviation of 1. So from the 0, we're going to go out 1 standard deviation both ways and get to 1. For the blue one, we're going out, we have a standard deviation of 2. So we're going to go out 2 to get to the standard deviation to the left and right. Because these have to have an area of 1 underneath them, so underneath these curves, because this pink one has a smaller standard deviation, it's going to have to be a little bit taller. So it's going to have a slightly different shape. So for our first couple of examples, it's asking us to find mu and sigma. So mu is just going to be your middle number. So we're going to have 2 for this first one. And our standard deviation is going to be the difference between 2 and one of these other numbers. Remember, your standard deviation will always be a positive number. So if you were to subtract the wrong way, so for instance, if you said 2 minus 5 and you got -3, you would know that was not correct. But to figure out the standard deviation, we can just do 5 minus 2 and we'll get 3. Over here, our mu is going to be 5. Because the mu is going to, or the mean is going to always be that middle number on your normal curve or your bell curve. And your standard deviation is going to be the difference between the mu and your next line that's drawn, or between any two of these. So from 5 to 7 is going to be a difference of 2. And for these two, we have a mu of 100. And the difference from one line to the next is going to be 15. So our sigma, or our standard deviation, is going to be 15. And for our fourth example, we're going to have a mu of 530, or a mean of 530, and our standard deviation is going to be the difference from 530 to 630, or 100. All right, so let's talk about the area under a normal curve. Suppose a random variable x is normally distributed with a mean mu and standard deviation sigma. The area under the normal curve for any interval of values of the random variable x represents either the proportion of the population with the characteristic described by the intervals of values, or the probability that a randomly selected individual from the population will have the characteristics described by the interval of values. So what this is saying is that if we were to go through and figure out the area under a curve for something that we're interested in, then that number is going to be describing the proportion of the population with that characteristic, or the probability that a randomly selected individual from that population will have that characteristic. For instance, if we had a normal curve, and we were discussing height, and perhaps we were looking for the area over here, and so this is less than average, so whatever the mu is here. If we have this area shaded, we would be looking for either the proportion of population of people that are less than this height. So for instance, if this is 5'7", and maybe this is 5'5", then this area is going to represent the proportion of people that are less than 5'5". Also, it means that if we were to randomly pick a person out of this population, that this number is going to represent the probability that we would select somebody under 5'5". We'll talk more about that in a little bit. First, let's talk about these different examples and if they could be modeled by the normal distribution. So for our first one, hopefully you can tell that this is got the higher part to the left and this little tail kind of trailing off to the right. So this is not going to be modeled by a normal distribution, and this is going to be actually skewed right. So if you have something that is skewed left or right, remember you're going the direction of the tail. For B, this also cannot be modeled by the normal distribution. And again, we could potentially describe this as being skewed right. And then for C, hopefully you can see that while it's not perfect, it's pretty close to the normal curve. So this can be described using the normal distribution. So let's look at an example. So here, this graph is showing us having a mean of 140, a standard deviation of 10, and then the area in red, this 0.3085, is the area under the curve, or to the left of 135. So if this was the price of a concert ticket, with the average being 140, and we have a 0.3085 for our probability, or the area under the curve, less than 135. So we could say that the probability that a randomly selected ticket at a concert of being less than 135 that was paid for it would be 0.3085. Or we could say that 0.3085 of the proportion of the tickets purchased for a particular concert were less than $135. So for instance, we would just say that 85% of tickets were less than $135. Or again, if we were to randomly pick somebody out of the crowd, we would have a 0.3085 probability of somebody having paid less than $135. So for example D, refrigerators. Suppose the life of refrigerators is normally distributed with a mean of 14 years and a standard deviation of 2.5 years. So it's asking us to draw the normal curve with the parameters labeled. So again, mu is always going to be in the middle. So mu of 14, and we have a standard deviation of 2.5. So we can actually go ahead and start labeling some of those. So if I'm at 14 and I go out 2.5, I'm going to be at 16.5 for the first standard deviation out. For the next standard deviation out, I'm going to be 2.5 above this 16.5, which will put me at 19. And for 3 standard deviations out, we will be at 21.5. And for mu, we're going to also go to the left. So 1 standard deviation to the left is going to put us at 11.5. 1 more standard deviation will put us at 9. And 1 more standard deviation is going to put us at 6.5. So here we have our normal curve drawn with our parameters labeled, and it's asking us to shade the region that represents the proportion of refrigerators that are kept for more than 17 years. Well, we don't actually have the 17 labeled here, but we're going to put where the 17 would be and then shade. So the refrigerators that are kept for more than 17 years, it's going to be this area here. And it's telling us to assume that the area under the curve is 0.1151, and it wants 2 interpretations for this number. Well, that means that if we were to randomly choose a refrigerator, the chances that it would last more than 17 years is going to be 11.51%, or a probability of 0.1151 that it will last for more than 17 years. Also, that the proportion of 0.1151 of all refrigerators will last more than 17 years, or that about 11.5% of refrigerators last more than 17 years.